All right, before I begin, I want to thank you. I want to express my gratitude for being in your company because it's such a joy to be with like-minded scientists and people who are using the scientific method to answer deep questions. And especially in times like this, I think we have to acknowledge how lucky we are that we get to participate in this journey of discovery. But also, I think it's important to appreciate the importance of science and the scientific method. So I would like to thank you for that. So today we'll talk about a topic that is very deep to my heart. And it's actually something that I started thinking when I was about 6 years old, and I haven't stopped since then. And the question is, what is the universe made of? And I want to tell you about the results that come. This is basically 2 decades of work from me and a group of friends and colleagues over the time. And we've been trying to answer this question that humans have been asking ever since at least recorded history started. So what is the universe made of? And I hope to highlight the importance of Keck in this journey of discovery. So I'll start with a brief introduction. You know, if we were earthbound beings, what would we think? But then astronomy opens up our mind and we find something completely bewildering and different. And then there are 2 questions that I'm struggling with these days. First of all, is the standard model correct? And second, even if it is correct, what is it, right? Because we talk about dark matter and dark energy, but what are they? This is the most profound question. And so what are dark matter and dark energy? And I want to elaborate a little bit on the role of Keck and the future regarding this. So if we did not have astronomy, if we're not able to look at the sky, this is pretty much what we would think the universe is made of. We would have accelerators, slamming things together, creating particles, and you would think that all there is to it is quarks, gluons, and the fundamental interactions. That's it, the standard model of particle physics. You may like it or not, but that's what you think the universe is made of. But then people start to look up at the sky, and they discovered that the standard model of particle physics doesn't work. Something is missing. And the best explanation that people have been able to come up with is something completely crazy. That the universe is made for the large part of 2 things that we don't know what they are. So one is dark matter and one is dark energy. They're called dark because they don't interact with light. That's as much as we know. And everything that we see on Earth, like on particle physics labs, is just 5% of the total mass energy budget. The rest is completely unknown. And I'm not saying this is the right answer. I'm just saying this is the best answer we've been able to come up with. So it's natural to wonder, is this lambda CDM model correct? Always have to wonder this. Are we missing something? And here there's something very interesting has happened in the past few years, which you might have heard of. It's called the Hubble tension. So imagine that you can measure this yellow curve is supposed to be the expansion history of the universe from the Big Bang to today. There's inflation, then deceleration due to dark matter, and then acceleration due to dark energy, okay? So imagine you're able to measure the conditions of the universe at about this time, say from the cosmic microwave background or from Big Bang nucleosynthesis. Then once you have a model, you can predict what this curve will be. It's very similar to throwing a baseball. If you can throw the baseball and you know the gravitational field of the Earth and you know air resistance and all that, you can compute how fast the ball will arrive and where it will land and so on and so forth. So we can do this exercise. And the other thing we can do is measure the expansion speed at late time today. And then we can compare the 2 numbers. And the discovery of the past few years is that these 2 numbers don't seem to match. Kind of like if I'm throwing a baseball and someone on the other side of the audience expected to land in some place at a certain speed and it lands somewhere else with a different speed. So if this were to happen on Earth, you would think that probably we don't understand gravity. Creating gravity in this circumstance. I might have been kicked out of Zoom. Sorry, people on Zoom. Okay. And so then we may think, okay, which one is it? So let me.
How's it look, John? Good? Bad? Okay.
So this is the idea. And okay, I can use this. All right. And so just to give you an idea, this is not like two measurements disagreeing. This is a number of measurements disagreeing. On the top left here, you see early universe measurements from a different combination of probes, from deuterium abundance to CMB, power spectrum, and so on and so forth. And this is a bunch of late universe probes, mostly the local distance ladder method, but there are also other methods. And these bands here are sort of the average of these two sets of measurements. And you can see the difference is not huge, is 8%, but it is significant. If you believe the error bars here, the tension is more than 5 sigma, which, even for a particle physicist would be something to take note of. Okay. All right, so this is kind of like where we are as a 2025. And this has attracted some attention. I found there was this article that came out on The Economist in August. And what I love the most about this article is this part here, cosmic horror. I don't know why they said cosmic horror. I find it very exciting, actually. It's like there's nothing horrific about this. Is actually how science works. Like we don't agree, and then we find out what's wrong, and we discover something. Okay, but anyway, this is something that I found amusing. So how do we solve it if it's true? So there's many ways. None of them make sense. But the ways that have been proposed, I think the two that make more sense are to try to increase the expansion rate of the universe before recombination. How do you do that? You can do it in two ways. One is include an early dark energy. This is not the usual dark energy. This is another dark energy. So there will be like 3 phases in the universe where something funky happens. Inflation, early dark energy, and then late dark energy. So this is not very natural, but hey, who am I to say what's natural? And then another way is to have new relativistic particles. This is a phase of the expansion history of the universe where expansion is driven by the number of relativistic species. So if you have some relativistic species, like a sterile neutrino or whatever, that comes in and disappears at the right time, you can make this happen. Again, this is not particularly appealing, but again, the universe doesn't seem to care what we find appealing. So this is the classes of solutions we're struggling with. And of course, from my point of view, I am an observer. I like to make measurements. So I like to find out whether this tension is real or not. Because in the past, people have been wrong about estimating their uncertainties. So I think the most important thing we can do before we conclude that there's a crisis in cosmology is to be very, very sure that this is indeed a problem with the universe and not a problem with our measurements. And so this is where we come in. And we've been using a method called time delay cosmography, which is completely independent of the CMB, of the local distance ladder, you name it. This is completely independent of everything. How does it work? It exploits a simple phenomenon called gravitational lensing. Imagine that you're looking at a distant quasar or supernova here behind the cluster or a galaxy. Then if the supernova or the quasar crosses a caustic, you get multiple images of your foreground, of your background object. Now, and this is true. This is like, this is a pretty good analogy. Galaxies are more similar to wine glasses, but this is more similar to a cosmic string, if you're interested. But the thing that you probably don't notice is that the other image of the fish appeared with a delay, because one of the images goes straight to us, the other one has to go around and has to go through more glass, and so it appears with a delay. And so this is the basic principle. You have a time variable source and an observer. One image goes one way, one image goes the other way. There's a difference in light path and also a difference in gravitational potential that slows down one of the sets of photons. And this gives rise to a time delay. And then from then on is basically trigonometry, some fancy trigonometry to convert, because you can measure this, you know, the speed of light. So you measure the time delay with the clock. So you know the length of this little thing here. And from that, you can reconstruct all the distances. And distances are the name of the game when you do cosmology. Once you have distances, you have the expansion history of the universe, you have everything, okay? So that's the idea. So in practice, what you do is you measure the time delay, you infer something called the time delay distance, which, like every distance, is inversely proportional to the Hubble constant and weakly dependent on omega matter, W, and so on and so forth, okay? So now, in practice, you need 5 high-quality ingredients. And this is pretty much like Italian cooking, okay? So you need a handful of ingredients, but they have to be excellent, okay? Otherwise, it just doesn't work. So in the 5 ingredients you need are time delays, and you need them to be precise to 2-3%. Astrometry, you need 10 to 20 millisecond astrometry. And Keck here has been amazing. You need to determine the potential of the lens. And again, to this same level of precision, we do this with HST, JWST, or KKO. Then you need to account for all the structure along the line of sight, because the universe is not exactly isotropic and homogeneous on small scales. And then there's something called the mass sheet degeneracy. I will not bore you with that, but it's a mathematical degeneracy in strong lensing. And to break this, we use stellar kinematics from Keck or JWST, and in the future, hopefully one day, TMT. All right. So about 5 years ago, I thought I could retire. So we had measured the Hubble constant to about 2%, and we were in very good agreement with the local distance ladder measurement from the SHOES team. And if you combine our measurement with the one from SHOES, you would get more than 5 sigma tension with the CMB and early measurements. Now, our uncertainty was about 2%, so our data alone were only 4 sigma, not 5 sigma, which is what I would like to be completely independent of. So that was it. That was very exciting. But then, like, you know, at this point, you start to wonder, and I didn't coordinate with Chaz here. Well, I think this may be the beginning of a new cosmological model. So at that point, you think, okay, look, at that point, you think, are we really sure about this? You know, let's think about it carefully, because we start saying that there's a new dark energy or a new particle or whatever. And, you know, the most important thing, extraordinary claims require extraordinary evidence. And so we thought, how can we verify the result? What can we do? And so we did something completely crazy, which is we threw away all the assumptions, basically saying we know nothing about galaxies. And then we tried to rebuild the measurement, replacing what we think we knew about galaxies at that time with data, with information. And the key data set here is stellar kinematics, the motions of stars in the lens galaxies themselves. Okay, you've had a preview of this from Sean Knabel's talk yesterday, but I'll give you the highlights. And the key issue basically is that we were able to use Keck and JWST and VLT to measure the motions of stars within 1% accuracy. The velocity expression was determined to 1%. That breaks the mass sheet degeneracy and another degeneracy called the mass anisotropy degeneracy, or MAD. So breaking MAD. And that gives us the Hubble constant, basically with very conservative errors. I'll skip through all the tears and blood and get to the 2025 results that we obtained in lambda CDM. So again, this is our measurements from time delay lenses. These are the ones from the most recent paper. What you notice here, they're all around 73, 74. So no matter what we do, if we change our assumptions, change our data, by the way, all these measurements are blind, so we don't know the answer. We write the paper without knowing what is the Hubble constant. Our only rule is that we're not publishing negative Hubble constants. So if the universe is contracting, we're not embarrassing ourselves. But every other measurement gets published. So we consistently find these high values of the Hubble tension, of the Hubble constant. And this is a summary of where we are with the Hubble tension in 2025. The early universe probes are here. The late universe probes are here. The one that stands out a little bit is this one by the Chicago Carnegie group. It's a little lower, but most of the other independent ones are higher. And I'm a little unhappy with this because the error bars are still too big. you can see that we prefer the higher number, but it doesn't rule out the CMB early universe probes to high level of significance, because by relaxing the assumptions, we have increased our error bars. So we're now at work to shrink the error bars, and I think we can get to about 1 to 2% in the near future. And I will not tell you how we're going to do that now, because I want to talk about another topic, which is dear to my heart. This is what's dark matter. So this, I have to say, sometimes when I think about what I would like to know before I die, this is what I would like to know before I die. I don't need to be the one who provides the answer. As long as someone tells me what is the answer, I'll be happy. So, so if you ask a theorist, they will say, this is kind of like what we think. So there's like, you cannot even read this, but there's like little Higgs, QCD axions, supersymmetric particles, extra dimensions, stereo neutrinos. There's like a whole zoology. There's no shortage of theoretical models. But we would like some evidence. And as observers, when we look up, this is kind of like what we have to deal with. How do we go from this to this, right? So this is the problem. One of the ways in which we do this is by looking at the properties of the universe on very small scale. So for example, if you take a cold dark matter universe, this is what the distribution of mass looks like. There's like a self-similar distribution with clumps all the way down to Earth size. If you introduce a different dark matter model that has non-negligible free streaming length, kind of like a kilo electron volt scale thermal relic or some sort of stereo neutrino, this erases scale below a threshold, and you end up with a much smoother distribution here. So this is sometimes reflected in statements like the abundance of satellites around the Milky Way and these sort of things. And you can quantify this in this way. Like in cold dark matter, the number of halos is a power law that goes all the way to Earth size, kind of like m to the minus 2. And in warm dark matter, it turns over like this, because you just have free streaming. The problem is that below a certain threshold, you don't expect potential wells to be deep enough to retain gas and form stars. So the key prediction of CDM is that most of these balls of dark matter would be completely dark, right? So in a cold dark matter universe, the Milky Way is surrounded by millions or billions of balls of dark matter that are completely invisible. So how do you see them? You see them through the gravitational effect. So we call them dark satellites or substructuring lensing. And the idea is that these introduce perturbations to the gravitational potential. And the most sensitive perturbation is the magnification of the flux, because it enters with the second derivative of the potential. So it's sensitive to structure on very small scale. But we can also detect it as astrometric, changing positions, or time delays. And the natural scale of this is a few milliarc seconds. So that's why we need AO to do this kind of work, because where the frontier is in the knowledge is at the milliarc second scale. Okay, so how do we do it in practice? So we need to choose the right emission from the lens quasar. So this is a quasar that is being lensed, producing 4 images. If you take the accretion disk, the UV hot accretion disk, that is too small for us. The reason why it's too small is that it's about a nanoarc second on the sky, so it gets microlensed by stars. And we don't want to know about the stars, we want to know about the dark matter. So you need to find a source that is about microarc seconds in the sky, or milliarc seconds, even better. And those are the sources that tell us about the structure of the universe on those scales. It's called millilensing for a reason. And so there are 2 regions we can use of an AGN. One is the dusty torus, so the region around the AGN that emits as close as possible to the sublimation radius of the dust. That's a very good source for us. And the other one is the narrow line region, that it's about milliarc seconds in scales. And that tells us about the distribution of matter in the universe on milliarc second scale. I think Maria showed this already. We can do this with OSIRIS. We can image lens quasars and measure the O3 flux ratios, and those tell us that there is something there that we don't see. We can detect dark satellites at billions of light years away, purely based on their gravitational effect. In practice, we don't detect one object at a time. We detect it statistically. And then we do an end-to-end comparison between the observations and the dark matter theory that we're trying to test. And to summarize the work in just one slide, the key result is, as far as we can tell, dark matter is consistent with the WIMP-like CDM particle, something like a 100 GeV scale non-interacting particle. And the lower limit on the dark matter particle mass is 6 keV, as far as we can tell, but of course could be much higher. But this rules out a whole bunch of theoretical models, say, of sterile neutrinos, for example. At most, 17% of dark matter is comprised of primordial black holes within our mass range, and we can probe somewhere between 10 to the 4 and 10 to the 6 solar masses. And we're working now on new limits on self-interaction cross-section between the dark matter itself that will appear, because we can characterize that too. So, and I think this is just the beginning. This kind of work is limited really in what we do by the number of systems we can follow up. And so far we've been limited to very few, partly because we don't know that many lenses, but partly also because we don't have the technology to follow them up. And with things like LIGO, we will be able to do this much, much, much better. Keck has played a major role in all of this. And I want to give a shout to at least 4 instruments, but I'm sure there's more. So we use, for example, NERC2 to get these beautiful images of gravitational lenses. We use OSIRIS to measure the spatially resolved fluxes of the gravitational lenses. We use LRIS and DEIMOS and to get redshift, because we also need redshift of the deflectors and sources. KCWI has been a game changer for us recently. We've been able to do spatially resolved stellar kinematics. With the thing that is so exquisite about KCWI is that it's so stable that we can really get to that sub% accuracy, which is what we need for our work. And this is a lens galaxy, and we've been able to measure how the stars move in here using KCWI. So all of this has been fantastic, and I think it would be getting even better in the next future. So what are we planning on doing? So we will continue to use KCWI, and KCRM helps us because it helps us go into higher redshift. And LRIS, DEIMOS, LRIS2, all of that will give us the spectroscopy we need. And Kappa, which is about to be commissioned and hopefully will enter science operations soon, is really going to be crucial for us because we need there are few lenses in the sky. And with the current AO system, we can only target a very small subset of them. We cannot choose the best ones that we need to choose. Kappa stands for all sky, so it increases the amount of targets. It also increases our Treu and our astrometry precision, which are things we need because we are always working at the limit of what can be done. And when LIGO will be ready, hopefully soon, that also pushes us down. And since we are at the limit, gaining sensitivity gains you numbers in huge factors because the luminosity function is very steep at this magnitude. So if you go like factor of 10 deeper, you get more than 100 times more targets that you can work with, which is really the limiting factor so far. In the longer run, TMT will be necessary because with Euclid, Rubin, and Roman, we are discovering already thousands of strong gravitational lenses, and we cannot possibly follow them up unless we have something like TMT. And so I think there's a path forward, and I think it's very dark, but in a good sense, dark matter, dark energy. But I'm so looking forward to it. And this would not have been possible without these wonderful people. Here are some of the people that have helped the most on the Keck work. I'd like to thank them, and I'm done.